Today our topic is working through and talking about how magnetic encoders can replace optical encoders and when that's appropriate and how we evaluate when that's a good decision. And we have Ted on the call today, who is our sensor expert at MPS.
Hi, yeah, Ted Smith. I am I don't know, FAE technical marketing engineer for the sensors in the US. So yeah, I'm looking forward to the discussion.
Yeah, well, thanks for taking the time to go through this. So Ted works with a lot of our customers on this exact situation where they'll have historically used optical encoders for applications and very comfortable with those. But there are many situations where it makes sense to use a magnetic encoder with a magnet as a replacement. And so
yeah, in
maybe you
general.
can talk about some applications or situations where that ends up being a really good option for the customer.
Sure. Yeah, that's we can start with kind of a high level and go down from there. But in general, if you need, let's say, 14 to 16 bits or less, magnetic encoders could be a good solution. And when you get up above 16, and I think we're starting to push the limits with technology, we may someday get to 18 bits. But beyond that, in these really highly specialized, very, very high resolution applications, optical will probably live for a good long time. Like I said, under 16 bits, magnetic's generally a good solution.
It's can you give some examples of those, like where the applications kind of switch, where just so people get kind of intuitive and understanding?
Yeah, sure, fair enough.
18-bit or 16-bit.
Yeah, you're right. Those are kind of esoteric numbers to just throw out there without any intuitive understanding. So let's say a lot of this has to do with robotics. I would say that robotics is the place where you start to see that transition in certain places between the, let's call standard resolution, which is 12, 14, 16 bits, and high resolution. And part of that depends on, let's say if you have an arm and you have, I don't know, a half-meter arm, and you need to, at the end of that arm, think of a surgical robot, you need to have micron or even just sub-millimeter precision. That means your angle error has to be extremely, extremely small because it translates over that length of that arm. And so there's some of those applications where I don't see anybody getting away from optical anytime soon. That being said, we do have magnetic encoders in most of these surgical robots out there. So there are things that can be done to increase the resolution or to let's say to supplement what the magnetic sensor can do, so you still get away with, and the surgical robots, obviously that's not usually a cost-driven solution. Those multi-million-dollar robots don't mind a few dollars. It's a size issue with those guys. They want to pack as much stuff as they can in each of those joints because otherwise the robot would just be giant. So I would say that's a good playground for where another place that I think that we'll see optical for a long time is in semiconductor manufacturing equipment, where you're tilting mirrors or masks at just 0.000x degrees, and that's a very, very high, very, very high resolution application where you just can't tolerate the extra noise. Almost everything else could be a candidate for magnetic angle sensing. Now, one of the, I think, non-engineering or non-technical hurdles is everyone's known about optical for a long time. People have used it. It's been around, and it's generally, I hate to use the word plug and play, but it's generally you have a module that you attach to the motor, pull a tab out, and you're good to go. Whereas it takes some engineering work with a magnetic angle sensor. You have to make some, run some simulations. You have to do some mechanical adjustments sometimes. You have to get comfortable with magnets. A lot of engineers, just haven't done anything with that since since grad school or undergrad. But that's the fun part of my job. I get to help out with those, and that's where I hopefully can be a pillar to lean on and support those types of applications.
And that's a good let's say lead into, I think we're going to do a webinar shortly about an actual design project where you're going to do kind of
walk through one a typical. There's no such thing as a typical, but we'll get as typical or as generic as we can get in a design, and look at some of the different things that we look at, the mechanical design and the choosing the magnet, even looking at, hey, there's magnet manufacturers here in the US, there's magnet manufacturers around the world, a lot in China, obviously. How do I even choose? How do I source a magnet? Those types of decisions.
Can you so back to the applications, can you just walk through, so we talked about ones where probably we'll always need such high precision that it doesn't quite fit, but how about ones where where you've seen good success, and even ones where it's it's a clear fit for this type of solution?
Yeah, I could kind of go through the various markets, but there's consumer, which generally the magnetic is a solution is attractive because of size and cost, but really cost. When you're making millions and millions of something per year, then a few cents starts to matter. You get into industrial, it's a good mix of cost and size. So things like, let's say, agricultural seeders or factory robotics or factory automation. And then the high end, like I mentioned with the surgical robotics, but you see all kind, factory warehouse robotics. That becomes, they make actually a lot of those, especially, the number, everybody knows how things are shifting from brick and mortar to online purchases. Those warehouses are just ubiquitous, and they make a lot of robots that move stock around. So again, it's a cost size thing, and we've been relatively successful in all of those markets. And then the big one is automotive. Automotive is cost driven, but they're also they like so-called diversity of technology, because it's a safety thing. We give ASIL for the automotive terminology, but yeah, it's you can use a magnetic sensor, you can use different you could use a magnet, and then you could use different types of magnetic sensors. So you could use Hall effect, TMR, AMR, all the magnetic magneto-resistive technologies, and get this diversity of technology, which increases the safety factor, because two completely different technologies have to fail in order for something bad to happen. So
that's, I guess, a new concept for me. So with an automotive, let's say they're measuring what could be like the throttle position, I suppose.
Yeah,
they might have a magnet.
One of the biggest ones is steer by wire, and just regular standard power steering, or
okay.
Yeah.
So they'll have a common magnet that would be on, let's say, on the steering wheel, and then they would have multiple sensors running probably to multiple controllers, and comparing what the actual measurements are, and if they see some
they don't match up, then we got a problem.
Yeah. So okay.
Yeah, that's the idea. So in a standard power steering, you actually have two places where you're measuring. You're measuring the steering wheel and the torque on that steering wheel, which is measured by a shaft deflection. And then you have the motors that are actually driving, helping the power assist. You measure the output of those motors. And so that's two magnets and then at least four sensors. So some companies will just do a dual die, and they have enough diagnostics in those dual die solutions that that's enough for the ASIL. Some companies say, no, we want this diversity of technology, and so two separate sensors with two separate technologies. But it's a lot easier to do that than to have two big, expensive optical parts in there, which are the exact same technology. And by the way, then can get, there's dust and dirt and things that can get in there. That's the other nice thing about magnetics, is we're immune to that type of stuff.
Yeah, I think the robustness and the reliability, especially one of those other applications you were talking about,
Yeah,
Agriculture is a tough environment. Warehouse is tough environment. Industrial is tough environment.
exactly. Yeah.
All right. How about so there are different types of encoders, at least on an optical side.
Sure.
Do you want to talk through typically what people are used to because they're making a choice on the type?
Yeah, yeah, and I think you're referring to the difference between an incremental encoder, which is essentially just a step. You don't know if you turn the thing off and turn it back on, you don't know where you're at, but sometimes you don't care. You just need to know, did something rotate a little bit? Um, so that's a so-called incremental encoder. Sometimes they'll have an index track, so at least once per revolution, you say, "Oh, I'm back home," versus absolute. And an absolute will have multiple tracks on an optical disc, and each incremental turn of some, depending on how many bits of resolution, how many tracks there are on the optical disc, each one of those incremental turns gives a completely unique value. So you could turn the thing off, rotate it some arbitrary amount, turn it back on, and it knows exactly where it is. And the nice thing about magnetic encoders, assuming that you use a dipole magnet, there's always trade-offs and we can do fun stuff, but the standard application for a magnetic encoder is true absolute. So you can turn it off, rotate, turn it back on, and it knows exactly where it is.
So the magnetic option would be analogous to an absolute encoder as far as
Exactly.
knowing where
Yep.
it is without having to do a home necessarily on
Yep.
power up.
Yeah,
Yeah.
and it's funny because we provide to make it easy to replace optical encoders. We provide A, B, Z, or ABI, the A and B track and the index or zero track. We'll provide outputs from the mag alpha from our angle sensor, magnetic angle sensor, that duplicate what you would get out of an incremental encoder. But you also can just read the SPI and see exactly where you are. So we can be kind of, let's say, backwards compatible with both absolute and incremental encoders.
Okay. How about the different technologies for a magnetic sensor, magnetic position sensor, magnetic encoder?
So the standard today, or I should say what has been the standard, is Hall. And the reason for that is that it can be, you can use a standard silicon process. So no special fabs, no special anything. Hall has a decent amount of white noise. So we're probably going to max out around 14 bits. You could get more, but at the expense of so-called dynamic bandwidth. In other words, you can keep filtering that white noise forever and ever and ever. So if you're rotating really, really slowly, you can get more. But let's say for a real world application, you're going to max out around 14 bits. To supplement that, the MR technologies, the magnetoresistive technologies, have been, let's say, growing in popularity. We have some competitors that use GMR, giant magnetoresistive. MPS has settled on TMR, tunneling magnetoresistive. And so our latest part uses a TMR. And that one today, for the same bandwidth that you would get out of our Hall, you get 3 extra bits out of our TMR part. And we think that we can extend that. We think that we'll be able to get it to 5 to maybe even 6 more, 5 to 6 bits over Hall. So another 2 to 3 bits beyond what we have in our current generation part. And then we'll start to hit the limits of that technology. That's, like I mentioned, 17, maybe 18 bits is really pushing the edge to the point where you just we'll then have to, that's where the fun starts. We get to think of kind of brand new technologies to keep extending and keep, we're trying to extend our reach as much as possible into the standard encoder field. And who knows, maybe someday we'll get to 20 plus bits
Of actual data.
Of actual 20 plus actual bits. So based on the noise, so that you can, we can talk about that later too.
What can you go just like a quick overview of because there's TMR, GMR, AMR as far as magnetoresistive technology. Do you want to just give the quick quick what the differences are?
Well, I'm not an expert on the magnetoresistive much. TMR I know quite well now because of our product. The biggest difference is the noise profiles of them and the sensitivities. So the reason that we like TMR over I would say the most ubiquitous is GMR. I don't see a lot of AMR, which I don't even know if I can remember. It's amorphous. I don't even remember. I don't remember what the A stands for in AMR. But anyways, so we see a lot of GMR out there. We decided on TMR, and the reason is it's very, very sensitive. It can handle a relatively high magnetic field range, dynamic range, so we can get down to single digit milliteslas, maybe 4 or 5 millitesla, and up to 100 plus millitesla. And the noise profile is quite nice. It's a so-called pink noise, 1/f noise. So it's well known and well characterized, and yeah, it works quite well for our spin axis. Going back to our basic technology, the way that we do our angle sensing is a little bit different than many of our competitors with the so-called spin axis. I wrote an article about it. You can find it. I think it was in Bodo's Power Magazine, which now got bought, but it's out there. Search for Ted Smith and spin axis. And the TMR works really, really well. It fits nicely into our spin axis technology, our time to digital conversion.
How about let's chat about how we're handling precision and repeatability and resolution. How we're validating our solutions and providing specs for customers so they can have the correct resolution for their application.
Yeah, resolution on the surface seems like a pretty simple, straightforward thing. You have a part, for instance, all of our parts, we have a 16-bit word that we output. So it could be easy to say, well, we got 16 bits of resolution. But that's simply not the case for all of our sensors. In fact, we have some sensors that are 8-bit sensors. That means that 8 of those 16 bits, the 8 LSBs, are just noise. They're just, you get a free random number generator with them. It would be disingenuous of me to call those 16-bit resolution encoders, because they're not. They have a 16-bit word, but only 8 real bits of information. And how we determine how many bits of real information we have for various parts. Again, we have parts that go from 8 bits up to that MA600, you can go to 14.5 bits. How we determine, how do you get 14.5 bits, for example? A bit is a bit, and you split it. And yeah, it's based on the noise of the sensor. So if you were to take the same exact measurement over and over thousands and thousands and thousands of times, you would get this spread of data, and it's going to be, if you did a histogram, it's going to be a nice Gaussian curve. And the idea is we want to know that if we have this Gaussian curve and we move a little bit over here, what's the smallest amount that we can move and be 99.97%, I believe is what the number is. It's plus minus 3 sigma, that we are measuring this angle versus this angle. If you get too close and you've overlapped and now you're only 60% sure, we don't consider that. We consider that you're below the resolution of the sensor. We need to be 99.97, 3 sigma, plus minus 3 sigma, sure that we've got 2 different angles, and that's what we consider resolution. And that goes back to, I think you can trace the roots of that back to A to D converters, and that's how AD converters were, how they determined what the resolution of the AD converter is. And it's a pretty conservative measurement. So if you look at our data sheets, and sometimes you compare them to some of our competitor data sheets, and you say, oh man, these guys say they're, this sensor is 12-bit. These guys have the similar sensor. They say it's 14-bit. What we found is that us and one of our competitors, and without naming competitors because I don't want to I'm not trying to talk bad about anybody some of these guys I think are doing it on purpose, so-called specsmanship. Some of them I think just honestly feel that it's a fair way to represent resolution, but I'm pretty confident that our conservative method is the right way. So if you compare, we know of one other company that does it the way we do it, so kudos to them. But we know of companies that just say, hey, our output word is 18 bits of resolution, or that's very disingenuous. Some of them, they'll say, oh, our digital grid. Well, they don't even say it, but they know that their digital grid, their actual digital measuring grid, which you want to be very, very small, smaller than your noise, so you can actually see the spread of noise. They know what that is, and they say, oh, well, that's our resolution. And it's not, because yes, you have these little buckets, but your noise spreads out over multiple buckets. So you can't just use the size of the little bucket to say that's our resolution. So yeah, like everything, if you're comparing sensors head to head, you can't just look at the data sheet and take it at face value. You gotta test it. And the good news is, if you test the MPS sensors, you're going to see that we're quite conservative with our resolution measurements.
Yeah, it's good to know that we are plus or minus 3 standard deviations away.
Yeah.
And so with that information, you can know that you'll be able to, within 3 standard deviations, tell that there is a change in movement.
An actual change in the angle. Yeah. Right. Yeah, exactly.
Right. Yeah, because it's independent of the word length of the amount of data.
Right. Right. Like I could say, hey, we could just start putting out a 32-bit or a 50-bit output word. Now, 40 of those bits would be noise.
Right.
It's not a 50-bit sensor.
Yeah. Yeah, you could put a 50-bit word for your 8-bit sensor, right? And you could say,
right, and then just say, oh, hey, look at that, 50-bit
sensor,
pretty good stuff. Resolution. Sell it for $50.
Right.
And, yeah.
Right. So in our well, anyways, I think that's a great example, great way to understand that for people. And so do customers typically know what resolution they need, or is that something you have to often help people with?
It depends. So you have a lot of times you'll have a customer, and we tend to work with both an electrical engineer and a mechanical engineer, because in order to get the correct field strength and the right linearity, the mechanical engineer has to place the sensor and the magnet in the correct orientation, and so we usually are involved with those two guys. And then there's usually a third party, for at least for the applications that are like servo or feedback control. So again, like a robot. And that'll be some controls guy. And that guy will usually say, hey, look, here's the dynamic bandwidth that I need and the resolution I need to make my controller stable. And so when you have a guy like that, it's pretty nice. You have a definitive number, like here's the bandwidth, here's the resolution, here's the linearity. If we meet those numbers, we're good to go. Some customers, to be honest, just aren't sure. This might be their first time doing any kind of an encoder project. Not even, they didn't use optical encoders in the past. This is the first time that they need to measure the angle of something, and they're not certain. And so in that case, we look at other, there's a plethora of different constraints that we look at to determine, okay, what resolution do we need? What linearity do we need? Do we even care about dynamic bandwidth? If something's going to rotate at some tens of RPMs, we don't care about bandwidth. But if it's a turbocharger that's going to be at 80,000 RPM, all right, we got to make sure that our latency and our dynamic bandwidth is good. So that's our first concern. So yeah, it's a process to figure those out sometimes. It's a luxury when they have the number that they can just say.
They just say this will work.
Yeah.
Can you talk about just the trade-off between dynamic bandwidth and resolution, at least that concept?
Yeah. So in Hall-based sensors, where the noise is white noise, Gaussian noise, you can take that noise. The front end of a standard Hall sensor is usually around 7 to 8 bits. But we have, like I said, 14-bit Hall-based sensors. How do we get from that 7 to 8 bits to 14? And it's simple. You just take a large window filter, and do some averaging. And so the more you average, the longer, the larger you make that window, the better your resolution will be. And the kind of rule of thumb is if you double your filter window size, then you get an extra half bit of resolution approximately. And so for a 14-bit resolution, I think we're taking 4,096, something like that, 4,096 points of data. And we output, this is the nice thing about our time to digital conversion, we output a new piece of data every microsecond. So that's very, very fast compared to the field. But that's still, when you're taking 4,000 of those, that's 4 milliseconds. And that means your filter window is 4 milliseconds. You make a change, an acceleration, because the filter has a velocity state variable in it. So it'll track velocity relatively well. But when you make an acceleration, it takes 4 milliseconds to fully catch up with that acceleration. So there's a latency in there. And it's a standard we can show. I think we've got a slide somewhere that shows, but it's a standard. It goes up, tries to track a step change, and then you get the kind of ringing, and it finally settles out. And that can be tough on control. So the way to get that dynamic bandwidth better is to scale back that filter, which means scaling back the resolution. And qualitatively, I can tell you, I have never been able to get a true servo, like a brushless DC servo motor, running with 14 bits of resolution. The dynamic bandwidth is just too low. On the edge is like 12.5 bits. You can do it if the control is really, if you really fine tune the control. Get down to 11 bits, and I've always been able to get a servo system working. So that gives you at least a qualitative measure of where you're going to be with Hall in that kind of servo feedback system. Again, you go to TMR, the tunneling magnetoresistive, our MA600 part, and you get a free 3 bits. So take that 11 bits, now you got 14 bits at the same bandwidth. And so we should always be able, I think I don't have enough experience with the MA600 yet. It's a brand new product, but my expectation is that we'll be able to do 14 bits, no problem, in a servo system that's running at, a standard, let's say 100 hertz or something.
So yeah, it sounds like there's not really an application, at least from a dynamic velocity changing acceleration situation, that that type of sensor would not be able to handle.
Right, yeah, but the trade-off, as there always is in engineering, is the lower resolution. So a lot of times, if we don't have that spec, one of the first questions that we'll ask is, what's the maximum acceleration of this system? And from there, you pretty much know what your dynamic bandwidth has to be, because based on that max acceleration, you can figure out your cutoff frequency that will give you a acceptable lag during that acceleration.
What kind of application would accelerate that? Would it even come close to that kind of acceleration?
So the one that I always go to, which is, this is not a common, this isn't super common, but the one that's always been crazy for me is turbocharger. We had one, it's a turbocharger, accelerates extremely quickly to an extremely high speed, 100,000 RPM, something like that, 80 to 100. I think it was closer to 100, which is insanely fast. To the point where, if you're running at that type of RPM, the balancing on the motor is so critically important, because you could rip your motor apart by just being slightly unbalanced. It's funny, we had, and you could probably still find these old YouTube videos, our very first demo with like our 2 generations ago Mag Alpha would spin up to 120,000 RPMs. We only had one of those because the demo itself was not that expensive, but we had to take it to a lab and get the shaft of the motor and the magnet on the shaft laser ablated to balance it, which costs like $5,000. And you would just see these tiny little laser ablation marks around it to balance it, because at 120,000 RPMs, the first time we did it, before we did the laser ablation, it literally just ripped the rotor, the motor apart.
Oh my gosh,
yeah.
So is it electric motor assisted turbo? Is that the application where you would have in okay.
Yeah. It's pretty
like in Formula One, where they have their
yeah. This was actually supposed to be a commercial product, and
Okay.
Yeah, I think they actually put it on the general market, on the open market, but
Nice.
not cheap, I don't think.
Yeah, no kidding. Yeah, if you have to balance like that, that precise. Yeah. Now that we have a, kind of baseline understanding of a lot of the, the underlying technology and the capabilities, um, there's still situations we talked about where it makes sense to use optical encoders. You want to just quick cover, when it would make sense to use an
Yeah,
optical encoder?
I think there's two or maybe three places where I would, if the resolution requirement is extremely high, um, again, well, today our max is about 14 and a half bits. I think we'll get to 18. Beyond that, optical encoders will get to live until we come up with some technology we haven't thought of yet. The other place is, there are certain, if you're looking for a module, cost is no object, and you're looking for a module, especially some of these encoders are ingress protection rated, IP rated. They're, I used to sell optical encoders in my previous life, and some of these things are $300-400 because they've got ingress protection rating. No water, no dirt, no dust gets in there, and it's just a module that you put it. Literally, you just bolt it onto the end and tighten a screw, set screw into the shaft of the motor. So those are the places where I think we'll continue to see optical for a while. The places where you see or used to see them in like in consumer and to a certain extent industrial. I think those are going to go away eventually because there's just the hill that you have to get over is this kind of like, well, we got to put in the upfront work, right? It takes, when you have an optical encoder and you just plug it on there, set screw, we know it's easy, we got it. And I go in and I say, hey, you should take a look at a magnetic sensor here. And customers say, yeah, magnetics. So I got to deal with the new magnetic material, and it's a new magnet supplier. I got to do some mechanical work. Obviously the output might be different, especially if you're using one of the, one thing I'll say for the optical guys is they did a good job of having proprietary communication protocols. So you'll see like INDAT, I forget, all of them have their own flavor, and they do it on purpose. So it makes it difficult to, so that's potentially a control change. But eventually the benefits are there, and the benefits are high enough that eventually customers are gonna have no choice but to say, okay, you know what, this year we're going to tackle this upfront work and save all the money on the back end. And a pitch for myself, that's the fun part of my job. That's what I'm here for, is to walk customers through that. And there's nothing I love more than getting a step file from somebody and, that says, hey, here's some mechanical constraints. Here's what we can do. Here's what we can't do. I run some simulations, send it back to them with some, and we iterate back and forth. That is literally the most fun part of my job. And it's really satisfying because at the end, we have something that saves the customer generally significant amounts of money. And now we have business. So it's classic win-win. It's what I like.
With it sounds like with optical encoders, if it's a, let's say, a plug and play smaller volume application, that's a reason, and there's not space constraints, cost constraints. If that's a small part of your bill of materials of your project, if you're doing a custom robotic arm, you're doing some custom machinery, an optical encoder is a reasonable solution in those situations because
I mean it's ease. If you don't have those constraints, if you don't have cost and you don't have size and you don't have then why put the work in to make the change if it's not right. But those are, we're relegating the optical encoders. I think now we're getting relegated to more and more niche space because what applications out there don't care about size and cost. It's not so many anymore. It's very specialized stuff.
So we've talked about performance, so bandwidth performance, resolution performance. We've touched on a little bit on the reliability aspect
Mm.
because maybe you just talk. I mean, people probably know with optical encoders, you have to keep it very clean inside internally to make it work. Where that constraint isn't part of our solution. What maybe just what you've seen with the reliability and aspect of comparing the two technologies.
Yeah. So the one disadvantage for I'll start with a disadvantage for magnetic, and then I'll qualify it, of course, is we are susceptible in most configurations to an high external magnetic field. So we have a part that's a differential part that can be used and will reject those external magnetic fields, but it can only be used on axis. So in other words, it has to be placed if the motor, let's say shaft, and the zoom is going to mess up but if the motor shaft is here, we have to place the sensor right on axis with the motor shaft. And maybe we'll show it. We could show a graphic or something there. But one of the things that we really like is the flexibility, mechanical flexibility of being able to place our parts inside shaft. And when you do that, we're now susceptible to external magnetic fields. And we have a number of ways that we can minimize that. And it's rarely an issue, but people don't generally carry around big neodymium chunks and hold them up to. But if you're
or your screen,
yeah, exactly. But if you're building a car and it's got magnetics in it, and you have to worry about, if someone does happen to have a neodymium magnet in their pocket, it can't cause you to veer off the road. So that's the disadvantage of magnetic angle sensing from a, let's say, robustness. That's the only one I can think of, and there may be others, but that's literally the only one I can think of right now. The disadvantage from a robustness standpoint of optical encoders is dust and dirt. So these things have these stripes that are very, very fine, especially if it's a higher resolution and a smaller encoder. And if you get a piece of dust in there and the VCSEL, the LED can't shine the light through the little slot, it misses a count. And that can be devastating, especially in an incremental encoder where you're counting each one of those. And if there's errors, position errors, and then you integrate those over time, they integrate to infinity if you don't have an index pulse. So it can be a big deal. Now, I mentioned they make these ingress protected encoders, and so that keeps all the dirt and dust and water out. But you're talking about three figures. You're talking about multi-$100 encoders when you've got ingress protection in there.
Yeah.
So with our part, you can cover the thing in dust, you can dunk it in muddy water, whatever you want. The magnetic field remains. The only thing that you couldn't do is, throw a bunch of iron filings in there, which generally isn't an issue. So from a robustness standpoint, I think we win pretty clear. And I really am trying to be honest and think of other, but I really think that we're pretty hands down winners there.
Yeah. So those are two of the typical three trade-offs people are making when deciding on a technology, right? Space, resolution, robustness, I suppose, is a third thing, but performance and size. Those are two common. And then cost is always part of an evaluation, even from an engineering standpoint, right?
Sure.
You don't get free reign on budget. You probably are typically given, some kind of for your part of your application, some or customers, I mean, for that part of the application, they're typically given some kind of guidelines, right? So what do you see?
It now? It's huge. And the more of a product that they intend to sell, the more important that cost is, to the point where customers will ask for fractions of a penny reductions because they're selling. Usually the typical volumes that we see from industrial are tens to hundreds of thousands, and consumer is hundreds of thousands to millions.
Right. So what's a typical, as we're talking about, these different applications, what's the typical cost difference? If you're talking to a customer that's currently using, this technology, let's say optical encoder technology, what kind of range, like percentage wise, are you typically seeing? Because you're doing this all the time with customers, and they're making that kind of decision. They're making a
Sure.
business decision along with an engineering decision.
Yeah. It's like I said, it's part of the spec. I don't, as the technical guy, I don't quote to customers, but if I pitch a great solution and then say, yeah, by the way, it's a $20 chip and the magnet's a $5, everyone goes, well, what'd you even come in here for? So these things in volume, and again, we've got a range of sensors, but you're talking, under $1 for many of our parts. The higher end parts like the MA600, the part itself, certainly under $2. And then the magnets, depending on the size and but a typical dipole disc magnet is might break the bank at 6, maybe 6.5 cents. So a solution, a typical 14-bit Hall-based solution, you're looking at right around probably $1 of total cost in there versus an encoder that could cost, depending on a lot of there's a super range if you need something that's highly robust and metallized and things like that, but you're not going to get much below $3 or $4 with an encoder, even if it's plastic and has a reflective mylar code disk. That's about as cheap as you're going to get. So let's say a 4 to 4x and up type of cost saving.
Okay, yeah, that's great. Yeah, so yeah, if they're looking at you might be a quarter or less on
Of
like
the
if
cost.
you just do the cost of what they're typically looking at. Yeah.
Mm-hmm.
Yeah, we'll have to.
Sometimes, like I said, that takes some upfront work. So there's some investment upfront because it generally takes some time, some engineering time and things like that. So to be fair, everyone's would look at that and say, well, then no one should ever use optical encoders. I agree, but the reason that they're still around in some of these applications is because that investment, that they're just, companies are running quick and they don't have time to make that upfront investment. And so that's the main hill that we have to get over. And once we do, it's funny, I tell our sales guys, once you get a design win one time, it opens the floodgates. And in fact, whereas with most products, you like these new designs, or you're looking for guys that have never done anything like this before, I actually get excited when we find out that a customer's been using a competitor magnetic angle sensor, because it eliminates that first hill. Like, oh, okay, they already have a magnet supplier. They're already comfortable with the magnetics. All we have to do now is show, that we're faster, higher performance, a little bit lower cost. It sometimes can be easier knowing that they have that magnetic experience in their belt already.
Yeah, so it sounds like there's a learning curve for companies the first time. So we'll have our we'll have that webinar that we'll put on in the future on how to get over, quickly get through that learning curve.
That's right. The idea.
Yeah. And what are you seeing once a company does do that first project and then they go to the second project? What, like, as far as is there still I'm assuming the design time for that aspect drops significantly. What's your experience with customers on the second version?
Yeah. So, usually the designs are unique. So there's still mechanical work and some things that need to be done, but you've already got a trusted magnetic supplier, let's say. You already know the basics of how our sensor works, the IO and maybe the tricks of, oh, I could put it in so-called side shaft next to the shaft, or I could put it side shaft orthogonal. Kind of what your degrees of freedom are. Customers know what I can do in terms of simulation and how I can help and how to basically best utilize my my abilities. And so it becomes, I would say, the first design at any customer is usually, because there's just things that they didn't expect. And I suffer from the I've been doing this for so long that you forget, you just think, oh well, yeah, of course everybody
Of
knows
course,
that.
you
And
wouldn't do
you're
that.
like,
Yeah,
oh yeah, no.
yeah, yeah.
Um, so I would say that the subsequent designs usually happen, in a fifth, 20% of the time that the first one does, just because that first one, there's a lot of other things to deal with,
Yeah.
and yeah,
Well, I mean, that's all. Those are all good. Let's say just kind of rules of thumb for people to understand. Where there's a huge cost savings potential when
mm,
switching. There is an initial learning curve and some investment in time that the engineering team will have to, and you clearly can help them out to get through that as quick as possible. Um, and
gotcha,
but
yeah,
in future projects they get the benefit payoff of not only the savings but then also the savings of the time on
exactly, yeah, yeah. It turns into
design
quite a
of it.
long term,
Yeah,
savings eventually.
yeah,
And it's nice for us because it's almost an annuity then, because you say, oh, okay, good. Now next design, hey, here's our next newest sensor,
right.
and here's the improvements. Oh, cool. Integrate that in, and it's yeah, it's nice for both sides, I think.
Yeah, great. Is there any? I think that's a great overview. Again, we'll plug our upcoming webinar on how we walk through an actual application design and the design process and thoughts that you go through. Are there any other closing comments for people to understand or think about?
Oh, let's see. I think we covered quite comprehensively. I can't think of anything else that we missed out on. I'm sure that we'll have stuff. People, I don't know if this people will be able to comment on this and ask questions. We can answer
Yeah,
those.
yeah. I mean, we'll chop out different pieces here as needed, but yeah, no, that was great. I mean,